Hello and welcome back. This is Computer Science 2, CSCE 156 and 156H. And today we're going to continue talking about algorithms and algorithm analysis. Remember that we do have a live Piazza Q&A. If you want to log in and ask questions during the lecture, go ahead. Otherwise, those will be archived afterwards. And of course, this recording will be available immediately afterwards. So to continue from last time, remember we left off with this 5-step process for algorithm analysis where you identify the input, you identify the input size, and we usually call that n because we're going to end up coming up with a function with respect to the input size n on how the algorithm behaves. The third step is that we're going to identify the elementary operation. Again, this is the most common or the most expensive part of our algorithm, and there could be more than one possibility there. Then we're going to determine how many times the elementary operation is executed with respect to the input size. That's where we're going to come up with our function that ultimately in step 5 we're going to characterize using asymptotics, big O analysis. Now, to motivate I'm going to go through each one of these steps individually, but to motivate that, what I want to do is I want to write another algorithm that you're already familiar with. We'll write it in pseudocode. Let's go ahead and rewrite an algorithm that you're familiar with, selection sort. Okay, so selection sort, basically, if you don't remember, it works by going through an array or going through a collection and selecting the minimum element and then moving it to the front of the array or front of the collection. Then now that part is sorted, so you need to go through the rest of it, find the next smallest element, and put that in the second position. Then you find the third smallest element, put that into the third position, etc. Right? So again, our tool for doing this is going to be pseudocode, because I don't want to actually implement this in Python or Java or C or something like that. You wouldn't end up implementing selection sort anyway, because it's a terrible sorting algorithm. And we're going to find out why, because we're actually going to start analyzing this more rigorously. So first of all, let's go ahead and identify the input. The input is going to be a collection of elements. And I'll give that collection a name, A. And I'll give each element in that collection a name, A1 through AN. Now note here again, I did not say that this was an array of elements. I didn't say that this was an array list of elements, a dictionary of integers or strings or anything like that. I'm keeping it as general and generic as possible. Okay. My output, I'll try to write a little bit bigger here, is going to be A sorted in ascending order or descending order. It doesn't matter. Non-decreasing and non-increasing order would be the proper terms for there. But I'm not going to get into those details, okay? But this will be in ascending order. How do you compare these things if you don't know what they are? If they're a collection or an array of numbers, well, then you could say that this thing is less than or equal to that thing. If it were a collection of students, then you would look at, oh, this GPA is higher, so it goes first, and this GPA is lower, so it goes second. Now, those are real engineering problems, and the way that they're solved in programming languages is by defining a comparator function or a comparator object. But this is just pseudocode. I don't want to get into those nitty-gritty details, so I'm going to keep this as generic and general as possible. Okay? So I'm going to go immediately into a for loop. And you can use traditional for loops here. I'm not going to declare an integer variable, int I equals 0, I is less than or equal to whatever. I'm going to just say that for I running from 1 up to, using an ellipse here, n minus 1. Now, I'm starting at 1 here because most programming languages do start their indexing at 0. I don't want to do that because I don't want to tie this to a particular programming language. There are programming languages, very few of them, that do have what's called 1 indexing. This is kind of a mathematical construct, and in math, we always start our indexing at 0, usually. So I'm going to adopt that convention, and I'm going to start at 1 here. Right? Again, good pseudocode will avoid language-specific conventions, keep things general, make liberal use of English and mathematics and mathematical notation in order to give you the idea of the algorithm. All right. The idea is that if you can explain it with pseudocode, then any competent developer, any competent coder will be able to take that and translate it to Python, translate it to Java, translate it to C, and use the idiomatic things in those languages to achieve what you're trying to do. I'm trying to keep this generic above any language. Okay. A min, that's our minimum element. I'm going to designate that as the ith element here, a sub I. Right? That's the minimum that we've found so far. And then what we're going to do is we're going to go through the rest of the remaining ones, and we're going to compare them to see if we can find anything smaller. So for that, I'm going to have another for loop. For j, running from, now if we start at I, we don't need to start at I here because we've already assumed that I is our smallest element. So I'm going to start it at I plus 1, and I'm going to run it all the way up to the last element, n minus 1, or n, excuse me. Remember, the elements are indexed 1 up to n. All right. Now, if the jth element is less than the minimum I've found so far, right, then I'll go ahead and update my minimum element. All right. To a sub j. Okay. Now, again, I am not using the equals operator here because some languages don't use the single equal sign to do an assignment operator. Instead, this is actually much clearer because I'm taking the thing on the right-hand side and I'm putting it into the variable on the left-hand side. I really like that. I know it's a matter of convenience on whether or not it would be more convenient to write it like this in actual programming languages. I won't even go there, but it was kind of a mistake to use the single equals operator sign as the assignment operator. All right? So this inner loop here is responsible for finding the minimum element among elements I up through n. Okay. Now what we need to do is we need to take that element and put it at the beginning, not at the beginning of the entire collection, but at the beginning of wherever you started, at I. So I'm going to swap a sub min and a sub I. Right? Now if this were a real programming language, then you would designate a temporary variable. You'd put one value into that temporary variable, you'd take the other value and put it back into that variable, and then you'd take the temporary variable and put it back into the other one, right? This would be at least 3 lines of code, right? Unless you were clever and you could get it done in 1 or 2 lines of code, but clever code is not necessarily the best code. But this, I'm making liberal use of English, plain old English. Swap a sub I and a sub j, okay? I'm also drawing vertical lines here to clearly demarcate my code blocks. Some languages use curly brackets. A lot of C-style programming languages use curly brackets to denote code blocks. Other programming languages don't. Python uses indentation and white space to denote code blocks. I'm choosing to do something completely different here to really drive home the point that this is pseudocode. This is not real code. You could get this effect in a typesetting system like LaTeX, and we might see that later. You could get this effect in a typical integrated development environment where you could actually collapse this, and there are vertical lines denoting the beginning of the block and the end of the block. Okay. At the end, I'm going to output A. Since it's been changed, it has it's now sorted, right? There is selection sort as a reminder. Again, good pseudocode, clearly labeled the input, clearly labeled the output, avoiding language-specific constructs. Anybody could take this and translate it to C, could translate it to Java or whatever programming language that you're trying to build stuff in. Okay? So this is going to be used as a motivating example for the remainder of these 5 steps here. Let me go ahead and transition back here. These 5 steps, we're going to want to identify the input. We're going to want to identify the input size, and the elementary operation, and then we're going to want to analyze that algorithm with respect to that input size in order to find out how many times that elementary operation executes with respect to the input size. All right. So let's start in detail with identifying the input. So again, this is generally given as part of the pseudocode, right? At least good pseudocode. If you've got bad pseudocode, that's an immediate pseudocode smell that you probably wrote bad pseudocode that you're not labeling what the input is, right? So if you've written good pseudocode, this part is basically done for you. But in some cases, the choice may not be clear. Right? In general, you only want to focus on a single input. And in general, you only want to focus on the most important input. So for example, linear search, we're going to look at that later on. Linear search has two inputs, right? An array, or a collection, I should say, and a key element, right? Now, which one of those two inputs is probably the most important? Well, if you look at, if you think that the input is just the one single key, then your input size is only ever going to be 1. And for a constantly sized input, there's really no analysis. It doesn't matter how big the array is. You could have an array size of 1 million or 10 million or 50 billion. And if your input size is 1, then you're stuck at this constant characterization of your algorithm. And we know that that's not the case. We know that linear search takes more time with more input. So the real, what you really want to focus in here on here is that you should focus on the collection. Right? Since it's the most important, that's really going to dictate the behavior of the algorithm. Okay, and this is another example. So you might not be familiar with it, but Euclid's GCD algorithm. The GCD stands for greatest common divisor. So given A and B, you want to find the greatest common divisor. And we can pull out an example off the top of my head. I don't know. Let's see. 60 and 12. Well, 12 divides both of those things, so 12 is the greatest common divisor. 10 and 5. 5 divides both of those things, so 5 is the the greatest common divisor. If you take two primes like 17 and 19, the largest common divisor with them, the greatest common divisor with them, is only 1. So finding that thing means that you're taking these two numbers and you're constantly dividing one by the other and maybe swapping them out or something like that. Euclid's GCD algorithm is an extremely efficient way of doing that. But there are two inputs, right? There are two integer inputs. So without loss of generality, you might have seen this in a math class or a discrete math class or something like that. It stands for without loss of generality. In other words, you're going to be making an assumption that is going to simplify your argument, is going to simplify your analysis, but that assumption is not going to kill your analysis. That you'll still have the general, the analysis that you're going to do is still going to have a general, it is going to still be applicable generally to the problem as a whole. In other words, that assumption is not going to simplify it so much that that all analysis goes away. Like if you had focused on linear search and you only focused on one input. So without loss of generality, you can focus on only one of the numbers, right? Generally, choose the larger, right? So if I were analyzing Euclid's GCD algorithm, what I would do is say, without loss of generality, assume that A is greater than B. So A is our input, right? Greater than or equal to, right? So A will be the input that we're going to focus on, right? So there are, I mean, it's a pretty straightforward step. Step 1, identify the input, but there are some gotchas there. There are some corner cases where you've got multiple things. Another example would be if you've got two collections, a collection of size n and a collection of size m, and you want to compute their intersection or their union or something like that. Well, without loss of generality, let's focus on one of them and we'll choose the one of them that's larger. And it's because if this is larger and this is smaller, then this one is going to dictate probably the behavior more of the algorithm. Okay, so keep things simple. Only choose one input and choose it well, and choose the right input. The second step is to identify the input size. Now, this one is also kind of simple, but deceptively so. It is a subtle, but important, and maybe tricky step, right? So we've already looked at a couple of algorithms here with different types of inputs. If the input is a collection, then it should be obvious that it's going to be the collection size. The size of the collection. That's the number of elements in it, right? That's going to be our input size, right? And that's why I've been designated in all of our examples so far as n. That if I've got a collection as an input and it goes 1, 2, 3, the ace of 1, ace of 2, ace of n, that's why I'm giving that last name, that last designation there, that there are n elements in the collection, because that automatically sets us up for this analysis. What if it's an image, right? An image has a height and a width, right? So a total number of pixels, you could say that it's a total number of pixels. Or choose the larger dimension. Basically, you want to simplify this as much as possible. So if I've got an image that's 100 by 1,000, well, probably if it's going to be 100,000 pixels total, and that could be my input. Or if it's 100 by 1,000 pixels, really long image, a letterboxed image or something like that, then I could say, oh, okay, without loss of generality, again, let's go ahead and assume that the input size is the larger of the two, so that I can go ahead and simplify my analysis. One of the trickier ones is, what if it's an input? What if it's a numerical input? That is an integer n, or integer x, I'll say, right? Or n. What's the size of a number, right? What's the size of the input of a number? Now, this is the subtle part, and I'm going to take a little detour here and present to you another example of why this is actually important. Okay, so come on over here. I've got what is called this. This is a variation on the sieve of Eratosthenes. It's a way of determining whether a number is prime or not. So given 19, that's prime. Given 20, that's not prime, because 2 divides it, 5 divides it, 20 divides it, etc. Right? So something is prime if it's only divisible by itself and 1. Otherwise, it's called composite. So what I've got here is an input, x, that's greater than or equal to 2. Of course, we don't usually consider negative numbers here. Or 1. So we're going to output true if x is prime, and we're going to output false if it's composite. Okay? So let's go ahead and take care of even numbers right off the bat. This symbol right here is a mathematical symbol that for division. If it were a programming language, of course, I'd use the mod operator, the percent sign in most programming languages. Or it would be a function call, modulo, right? If 2 divides x, then output false, okay? Because it's an even number, and even numbers are automatically composite, except for 2, of course, is prime. So maybe I want to change this, and so this is strictly greater than 2, right? Or just take care of that by itself. 2 is, of course, prime. That's just an edge case, a corner case that you have to take care of by itself. Otherwise, I go into a loop here. For each for each odd number, 3, 5, 7, 9, 11, etc., all the way up to the square root of x, by values of 2 here. I'm going to skip them by 2, so I'm not testing all those even numbers over again. If it's divisible by 2, of course it's divisible by 4. Now, I am doing some extra work here in that I'm testing 3 and 9. Is x divisible by 3? Well, if it's not divisible by 3, then it's certainly not divisible by 9. So I am doing some extra work here, but that's just to simplify this. The real sieve of Eratosthenes doesn't do the extra work. It goes through and cuts out all the numbers that are divisible by 3. Then it goes through and cuts out all the numbers that are divisible by 5 until you get down to the sieve where it's just the prime numbers, right? But this is a little bit different. If d divides x, then of course output false because it's not prime, because I found a number greater than or equal to 2 that divides it. Otherwise, if I get through this entire thing, and I only have to go up to the square root of x here, by the way, because the square root of x, if there's a divisor on the that's less than the square root of x, then there's a corresponding divisor that's greater than the square root of x, and those actually match each other. And so I'd only have to go up to the square root of x here. I don't have to go any further. If nothing divides it from 3 up to the or from 2 up to the square root of x, then nothing greater than that will divide it. All right, that's just basic math. Then I output true if after testing all of those divisors, none of them divided it, then it's definitely prime. Okay? So what I want to do now is I'm going to go ahead and transition over, and let's take a look at a program that does this. Okay? So this is this demonstration is gonna match our intuition about how algorithm analysis should work, and in particular the second step of choosing the input size. Okay, so let me go ahead and run this. This is an implementation of that algorithm that I just presented over there. We take a big integer x here because otherwise any demonstration on very small numbers is going to be immediate. I check to see if it's divisible by 2 and output false, of course. And of course I would have to take care of 2 itself. Then I compute the square root of x. I have I here which starts at 3, and while it's less than or equal to the square root of x, then I test that to see if I divides it. I called it I here, and I called it D over in my pseudocode. If after the modulus operation it equals to 0, in other words, it has a remainder of 0, then it is not prime. It is composite because I divides it, and so I output false. And then I increment up by 2. All right. Otherwise, if I get done and tested all the potential divisors and none of them divided it, then it's prime, and I output true. Okay. Here's some examples. So here is a 10-digit prime. So if I run this, it's going to be pretty quick. It is true. It's true that it's prime. Okay. What happens when I increase the magnitude of that number? So this is a 15-digit prime. And let's see, how long does that take? Well, not too long, but noticeably longer, right? Okay. So what happens when I have a 100-digit prime? So I went from a 10-digit prime to a 15-digit prime to a 100-digit prime. Okay, and this is definitely prime because I generated it that way, and I verified through other means that it was prime. And we'll just let this go. Let this keep working in the background here. All right. So what is the size of the input of a number x? The naive way of looking at this is that the size is 1 because there's one number, right? Well, that's not how things work. As the number gets larger and larger and larger, it takes more digits to represent that number. And that's what I was capturing over here in this demonstration. A 10-digit prime this algorithm runs faster on that 10-digit prime and slower on this 15-digit prime, right? So for a number x, or an integer x, it should be the number of digits it takes to represent x, right? But now we're humans, so we immediately think of digits. But ultimately, it's going to be run on a computer. And a computer doesn't think in base 10. We think in base 10 because we have 10 fingers and 10 toes, at least the luckiest of us. But a computer doesn't have 10 fingers and 10 toes. It has zeros and ones. So I'm going to change this to the number of bidgets it takes to represent x. Right? And we don't call those bidgets, but that's what they originally were called. We call those bits. the number of bits that it takes to represent x. Because if I've got a small number, it takes fewer bits to represent that number. And if I've got a large number, then it takes more bits to represent that number. To write it down and then actually put it into a computer as input. That's our input size. Okay? So the question becomes, how many bits or digits does it take to represent x, an integer x? Right? Okay. Now for this, we're already in a digression here. I'm going to take yet another digression so that you have some review of this. Hopefully you're able to answer this immediately, but if not, then this will serve as a good review here. All right, so I'm not going to talk about bits just yet. I'm going to, and I'm not going to answer the question directly. I'm going to answer the reverse direction. All right. So given a number of digits, ... So if I gave you 1 digit, or if I gave you 2 digits, or if I gave you 3 digits, etc., what is the maximum number you can represent? And again, we're talking digits here. So if I gave you 1 digit, the largest number that you could represent is 9. Right? You can't represent 10 because that takes 2 digits. You could represent 7, but that's less than 9, right? What about 2 digits? If I gave you just 2 placeholders, basically, well, fill those with the largest numbers that you can think of, and that's 99. Right? Likewise, if I gave you 3 places, 3 digits, then it would be 999. Right? ... What if I gave you k digits? What's the largest number that you could represent? Well, if it's 999, 999, you see the pattern here. It's going to be 10 to the k minus 1. Okay? Now, this was not the original question. The original question was how many digits does it take to represent a number? In other words, it's working backwards. If I gave you x, then I want the number of digits over here. Right? So this is just mathematics at this point. This is just algebra. That if I've got x, the maximum number that I can represent with that is 10 to the k minus 1. And if I've got x, I want to solve for k. In other words, I just need to bring everything over to the other side and get k in isolation here. That means that I'm going to take 1 onto the other side. And now with only 10 to the k, how do I get rid of that 10? I take a log, base 10, and that cancels, the k comes out front, and that all cancels, right? So in other words, log base 10 of x plus 1. Now, we don't like constants. We don't, and in fact, we don't like base 10 because we are computer scientists. If you're a regular old normie, a human person, then yeah, you count everything in base 10 because you got 10 fingers and 10 toes. If you're a mathematician, you count everything in base e because that's the natural base, because all of those annoying little coefficients go away when you take the derivative, right? But we're computer scientists. We don't like base 10. We don't like base e. We like zeros and ones. We like not digits, but bidgets or bits. Right? So if I gave you a number of bits, what is the maximum number that you can represent? All I need to do is go through the same exercise here. If I gave you 1 bit, well, then it'd be 1. If I gave you 2 bits, then it'd be 1, 1, which corresponds to 3. This one corresponds to, of course, 1. If I gave you 3 bits, 1, 1, 1 is the largest number that you could represent, which is 7 in binary, ... If I gave you k bits, then the largest number that you could represent is 1, 1, 1, ... 1, 1, in other words, with k ones. And without going into too much detail here, this is 2 to the k minus 1. Exact same pattern as this. It's just a different base, right? Normal humans go with base 10. Computers go with base 2. And so to work backwards here, if I've got x, how many bits does it take to represent x? Well, now it's the same logic as before, the same process as before, but the base is different. Log base 2 of x plus 1. Right? Or roughly just log base 2 of x. Right? And that's what we're going to go with here. Forget about that 1 because ultimately in step 5 we're going to ignore those coefficients, so it doesn't really matter. Okay? So how many bits does it take to represent an integer x? It's going to be log base 2 of x bits, roughly. Right? Now you could take the ceiling on that, you can take the floor on that, and come up with a simplified version of that. But that's going to be our input size. It's going to be n is equal to log base 2 of x. Right? Why is this important? So to understand that, I'm going to go back to my sieve of Eratosthenes here. And by the way, let's check in, see if it's running. It's still running. Right? I wonder how long it's going to run. Let's go ahead and go back to the algorithm here. Okay. Now, if you were naive about this and you said that the input size is 1, that's clearly wrong, because doing this algorithm on a 10-digit number, we got our an immediate answer. Doing this on a 100-digit number, it's still going after 5-10 minutes here. So that's wrong. What if the input size is, well, x itself, right? X, or the magnitude of x, right? Or I don't want to write it like that. What if it's x? In other words, what if it's if it's that I don't even know how to say that huge number there, but you would say that the input size is x itself. Right? Well, if I analyze this loop with respect to x, then I would say that the loop executes square root of x times. And I'm still not wrong on that, right? That is actually true. But if that's my input size, ultimately I would come to the conclusion, if this is my input size, then I would come to the conclusion that this the sieve, I forget how to spell it too, sieve of Eratosthenes is a less than linear algorithm. Kind of like what we were doing last week with our first example. The first example that we did, unfortunately now I forget what it was. It was just summing things up with a linked list, right? That was linear. With an array-based list that was linear. In other words, it examined every single thing in the collection, and so we would say ultimately that it's order n, that it's linear, right? And if you double the input size, then that means that it's going to double the amount of work that you have. But this is absolutely wrong, right? If instead we do the correct analysis and say that the input size is log base 2 of x, then how is this loop performing? Square root of x, it executes roughly that many times divided by 2, technically, whatever. Forget about those small little details here. Well, clearly that's not my input size here. I need to translate this to my actual input size. To do that, what I need to do is solve for x. So I'm going to actually reverse the analysis that I just did. X is equal to get rid of the log here, this is 2 to the n. Right? So if I plug that in over here, then this is going to be the square root of 2 to the n. Does that look like a linear function to anybody out there? Absolutely not. Hopefully not, right? Otherwise, you need to go back to algebra here. This is exponential, right? And this is not fully exponential, it's slightly sub-exponential, but it's still huge, right? N is my input size. With the example that's running in the background right now, n was 100 digits, right? N is equal to the number of translate that to bits, is equal to 100 digits, right? And now you understand why it's still running. This is going to end up being 2 to the 100 roughly, right? In fact, let's actually figure it out. I've got Wolfram Alpha in the background here. Let's go ahead and find out how many bits that this number, this huge, this 100-digit number here, how many bits does it take to represent that thing? So log base 2 of 10 to roughly the 100, right? It's base 10, they're 100 digits. So that's going to be 332 digits. We'll go ahead and round down, right? So in other words, square root of 2 to the 332 bits, that's how many operations are going to end up being performed. Divided by 2, go ahead. In fact, divide by 1,000 if you want, because this is astronomical. Even if you said that there were 100, let's say 1 billion operations per second. So there's 1,000 million, 1 billion operations per second. That is going to give me that many seconds, okay? Seconds. That's that many seconds. So how many hours is that going to take? There are 3,600 seconds in an hour. That's how many hours it's going to take. Well, how many days is that? 24 hours in a day, 365.25 days in a year. That's how many years it's going to take, right? 10 to the 33rd. 3 times 10 to the 33rd. All right, fine. How many millennia is that going to take? Still 10 to the 30th. I don't know what number that is. It doesn't have... Let's see. Does it describe what that number is? There is a name for it. Okay, usually Wolfram Alpha comes up with a name for it, but oh well. You're talking about the heat death of the known universe or something like that, right? So should I continue doing this and letting this run in the background? Probably not. I'm going to go ahead and stop it right now. Right? So to bring this all back, why is this important? It's important because seemingly simple algorithms can have bad analysis if you misidentify the input size, right? So you still have to be careful on the second step. Those are the first 2 steps. Identify the input size. Now, what about the elementary operation? Right? So this is a subtle, but this is also subtle but important. But basically, you're wanting to ultimately, you want to characterize the algorithm's complexity, the amount of work it does. Well, then obviously you need to identify what work means. Right? So in general, you choose the most common or expensive operation. But in general, you exclude things that are necessary for the execution, the control structure of the algorithm. All right. So we'll come back to some examples here later. What I want to do now is I want to go back to our selection sort, and I want to run through those first 3 those first 3 steps here. Okay. So here's our selection sort algorithm. We've got 2 for loops. We've got a lot of operations here. Let's go ahead and go through the first step. Well, the first step is already done for us. Our input is going to be the collection A. What is our input size? The number of elements in the collection n. Right? That's why I labeled it that way. Good pseudocode will have half of the work done for you. 3. What's our elementary operation? Elementary operation there. There are lots of things that we could choose from here. For example, in our for loops, we've got an assignment. On every loop, we've got an assignment of our index variable here, I. For every loop, we've also got a check to see are we done executing this while loop, right? For I equals 0, I is less than n minus less than or equal to n minus 1. That comparison there is some non-trivial amount of work when you're thinking about processor time, when you're thinking about CPU cycles. I'm not saying that that it's free or that it doesn't cost you anything. In the end, we also have an addition here, because it goes from I is 1 plus 2, plus 1 is 2, 3, 4, 5. There is an addition, there's a comparison, there's an assignment operation with just this for loop. But that's necessary for the control structure of the algorithm. We generally don't want to focus on those things. The real work of the algorithm is done somewhere inside of a loop, right? What about this assignment? Well, this is not the most common thing. There's still an embedded for loop inside of this, so that's probably not where we want to look either. Again, we have things that are necessary for the control structure of the algorithm, this loop where we've got an assignment, an addition, and a comparison on every single iteration. We're gonna ignore that stuff though. Here's where the real work happens. We do a comparison here to see, is this thing smaller than the thing that we found so far? If so, that's going to be our new minimum. Right? That comparison right there is probably a good candidate. So, but let's look at the rest of the algorithm first. An assignment, that's not even the most common thing, because if this comparison here evaluates to false, then this never even happens. This is the most common with respect to these two for loops because it's the innermost operation, right? That this loop executes a number of times for every time that this loop executes, and the operation inside of that executes every time for that for loop, right? Another candidate down here is a swap. And if you've got an engineering problem where swaps are more expensive and you want to, and you've got an engineering consideration where that is an issue, then absolutely you should go ahead and analyze this algorithm with respect to swaps. One real-world example is memory accesses. Memory accesses might be more your real bottleneck, and that might be more expensive overall. Or an embedded system where swapping out two memory locations is way more expensive than a simple comparison, because a simple comparison is done on the processor itself, whereas a memory swap location, you're accessing much slower memory, and that would be more of a bottleneck. And I've seen real engineering applications where they chose a less efficient algorithm with respect to comparisons, because their engineering problem said that we need to minimize the number of memory writes or memory reads, so we can't do that. We need to analyze it with respect to swaps. But swaps would certainly be another candidate there. But what I'm going to do is I'm going to say the comparison. And this is why a good pseudocode will also number its lines. 1, 2, 3, 4, 5, and 6. Okay? Comparison on line 5. That's what I'm going to go with. Again, it's not wrong to say swaps. It would be kind of wrong to say additions because of your control for loops here. Technically, it wouldn't be wrong because that is something that you're doing, but ultimately, for every addition, we're going to have a comparison anyway. So if I've got 50 additions, I've also got 50 comparisons. Those 50 additions are going to be subsumed in some coefficient in my final analysis. So make sure that you're choosing the most common or the most expensive operation overall, right? That could be a comparison. That could be an arithmetic operation like an addition or subtraction, or multiplication or division or something like that. Or it could be, like in the case of a linked list when we were looking at last week, the act of traversal. So moving from one node to another node. That could be our elementary operation. Okay? All right, so let's go back over here. We'll come back to this, though, because that's going to be our running example throughout the day here. All right. So examples, of course, would include comparisons, especially if it's a searching or sorting algorithm, or arithmetic operations like addition, subtraction. In fact, I'm going to go subdition/subtraction. Why? They're the same operation. Subtraction is nothing more than the addition of a negative number. Multiplications or divisions, right? And why do I put those together? Because, well, a division is nothing more than a multiplication by a reciprocal, right? So those are kind of the same operations. If you were looking at an addition versus a multiplication, of course you would choose the most common one, but all things being equal, multiplications are going to be way more expensive on modern hardware than they are than our additions, right? Depending on how they're done. Or if you've got a graph or a list, you might say node traversals examinations. If you're at a particular node in a linked list, then the processing of that node, whatever that processing means for your particular algorithm, right? Okay. Our fourth step is analysis, right? And again, the way I'm just going to cut and paste what we had from above. Ultimately, what we're going to do is we're going to want to analyze the number of times the elementary operation is executed with respect to the input size, because that's going to capture the amount of work. If I've got a collection or an array of size 100 and we end up doing 1,000 comparisons, then that's the kind of relation that I want. For an input size of 100, I'm doing X comparisons. I'm doing some function of comparisons. That is, we want to produce a resource function. This resource function is going to be a function, or if it's time, you can call it t. I'm just going to call it f here. It's going to map the natural numbers to the real numbers, right? Natural numbers to the real numbers. Now, that's just a mathematically technical issue here. Why natural numbers? Natural numbers are 0, 1, 2, 3, 4, the non-negative integers basically. And why n is captures the input size. Right? There's no such thing as an input that's 5.5 large, right? That's why we're restricting it to integers. There is also no such thing as a negatively sized input. If I've got an input, it could be empty, like there's an empty list or an empty set, or 0, the empty number, if you want to call it that. I could certainly talk about those empty inputs, but what's the size of what is a list of negative 10 elements look like? It doesn't make any sense. That's why we're restricting our domain over here to the natural numbers. That captures the input size. R, in fact, the positive reals to the positive reals, R plus, that captures the amount of work, right? And we restrict that to the positive domain because there's no such thing as a free algorithm, or there's no such thing as an algorithm that pays you. Imagine Bitcoin mining that produced energy. It doesn't make any sense. You're using energy to execute an algorithm to mine Bitcoins, right? And that's why you do it on other people's dime, right? You do it so that you're not paying for the electricity, because the electricity, at least at certain points, probably still, Bitcoin is not valuable enough that the amount of energy that you expend on it and the amount of hardware that you pay for it means that you're making money anymore, right? If energy costs are higher than the value of the bitcoins that you're mining, then you're losing money because you're expending more on your power. But of course, if somebody else is fitting the bill, then you're all good. And don't try that on CSE, by the way, right? But there's also no such thing as negative time, right? Imagine, I mean, maybe in the quantum world you could do this, but imagine starting your algorithm and then having your answer 10 days ago, right? It doesn't make it somehow the computer time traveled and gave you the answer before you even started the process. That's why we're not considering negative numbers here. It's going to be we're trying to capture the amount of work here, and that's what this function is doing, right? It may require a calculation of summations, right? Finding closed form solutions, or more complex math, right? In fact, The vast majority of real algorithm analysis is done using very, very advanced mathematics or using identities and stuff like that. We're going to keep it simple though, and at most we're going to be using basic summations, all right? And just like we did last week, I wrote it down for a linked list to an index-based find to sum everything up. Well, for the first iteration, I did one traversal. For the second iteration, I did two traversals. For the third iteration, I did three traversals, et cetera, et cetera. And I said, well, how many total traversals did I have? 1 plus 2 plus 3 plus 4. That was a summation. And from that summation, I found a closed form solution by appealing to Gauss's formula. Okay, and that's the way that we're going to proceed. In general, you want a worst case analysis. Right? And you want to provide an upper bound on the amount of work your algorithm will perform. And we're going to look at several examples here where you could get lucky. And the very first, like for example, linear search, you could get lucky and they find it at the very first spot that you were looked. In which case, you can ignore everything else and stop. And the best case analysis would be one comparison. That's not really a realistic portrayal of how your algorithm runs. Just like over here, the sieve of Eratosthenes here. What if we got lucky and the number was even? Right? Remember that this was going to take several universe lifetimes to actually execute. Well, now it executes immediately because it got lucky. It said, "Oh, well, this is even, so 2 divides it. So clearly, it's not prime. False. I'll stop. I won't. It never even got to this while loop down here because it was able to find it. Or what if it's divisible by 5? Right, the second number that we check in that loop. Well, you're just getting lucky there, right? It's not like your algorithm is always going to perform lightning fast like that. You don't want to take advantage of that and give a false sense of positivity that this is a good algorithm. This is a terrible algorithm, right? So in general, we're looking for a worst case analysis. You want the worst possible situation so that, yeah, okay, it might perform better in some cases. It might even perform better on average. There is average case analysis. But ultimately, we're looking for the worst case scenario here, okay? So what I want to do now is, for the remainder of our time, let's go ahead and analyze selection sort, and then we'll also do a couple more examples. So let me go ahead and transition back over here to the overhead. Now what I'm going to do is I'm going to analyze how many comparisons. This is my comparison. This is the thing I want to know. How many times is that comparison actually performed? I could write a program and I could increment a counter every time this line is run, right? Put a counter right on line 3.5 and count how many iterations are actually done with this. And I could run this over and over and over again and maybe find a pattern or something like that. That would be empirical analysis, actually running something, benchmarking it, counting up the number of operations that you're looking at, etc. I want to solve this problem once and for all. I just want a function. I want a function that looks something like a summation like we did last week. So what I'm going to do is I'm going to work from the inside of the algorithm and work outwards. Right? So the first question is, how many comparisons are performed on line? Oops, sorry, it should be 1, 2, 3, 4. So it should be line 4. There we go. There we go. So how many comparisons are executed on line 4? Just looking at line 4 in isolation. Right? Well, there's only one comparison. If I just look at line 4 in isolation, then I'm ignoring the loops. I'm ignoring the fact that this is nested inside of a loop. And I'm saying that there's one comparison on line 4. Okay? Now let's expand this out a bit. Line 4 is executed a certain number of times with respect to the loop on line 3. How many times is it executed? It's executed once when j is I plus 1, I plus 2, I plus 3, I plus 4, I plus 5, etc., all the way up to n. I don't know what that is off the top of my head. I'm going to you might be able to determine that off the top of your head, n minus I or something like that. I'm going to save that analysis. I'm going to write a summation here. For j, running from I plus 1 up to n, I'm going 1 plus 1 plus 1 plus 1 comparisons. One comparison when j is I plus 1. When it's I plus 2, then one comparison. I plus 3, one comparison, dot, 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 until it gets all the way up to n. I'm just going to keep that in summation form here. That all is from line 3. Now I'm going to expand it out even further. How many times is the code block on line 3 executed with respect to the loop that it's embedded in, or nested in, on line 1? Again, go ahead and come up with a summation. For I, running from 1 up to n minus 1, this entire thing is summed. And of course, you can put parentheses there if you really want to, but it kind of messes it up. In fact, you don't even put parentheses here. Right? Summation of summation of summation is perfectly fine. And now this is line 1. So I came up with my summation. Great. That doesn't give me an easily closed. This is not written in closed form. What I want is just a simple answer of n squared plus n minus 3 over 2 or something like that, right? That's what I want. Right? So what we're going to do now is we're going to take the second step, and we're going to find a closed form solution of this thing. Okay? All right. Let me go ahead and rewrite it. In fact, let me get another pen here. Let's see if there's a better one. Nope. I will invest in some Sharpies. Here's nice, but I'm going to switch over to blue here. So here's a summation from before of I running from 1 up to n minus 1. And then an inner summation here of j running from I plus 1 up to n. And what we're summing is 1. So let's go ahead and focus on this inner summation first here. Okay? This inner summation is 1 plus 1 plus 1 plus 1. How many times? Well, if you look at this from the following perspective, I plus 1, I plus 2, I plus 3, dot, 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 up to n. Right? You're doing 1 plus 1 plus 1 plus dot, 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 plus 1. Right? How many ones are there here? Okay. Well, it's kind of difficult to tell off the bat unless you're good in the head with math. What if I extended it all the way over here from 1, 2, 3, dot, 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 all the way up to I, and then I plus 1, I plus 2. What if I completed the summation here, the series? 1 plus 1 plus 1 plus dot, 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 1 plus. Right? Now, this is what we're interested in, but this is what's easy. How many ones are there here? Well, there are n of them because I started at 1. Right? How many ones are there here? Well, all I need to do is find out how many ones there are here, take the total number, subtract off that number, and I get the number of ones over here. How many ones are there here? Well, 1, 2, 3, all the way up to I. There are I ones here. So how many ones are there over here? You just have to take off the ones that you skipped. So this is going to be n minus I. Right? It's going to simplify to n minus I. So don't lose your outer summation here. I is equal to 1, n minus 1. And it's going to be n minus I on the inner summation. Right? Other tricks that you can employ are the sum of summations is equal to the summation of sums. In other words, you can break this up into two summations. I equals 1 up to n minus 1 of n. This is a summation, and I'm just taking the negation out front here. I is equal to 1 up to n minus 1 of I. Right? So I split it up because this is a summation. It's just n plus negative I. And so the summation of sums is equal to the sum of summations and any other tricks that you can employ from your algebra. Right? This one's pretty easy. It's n plus n plus n plus n. How many times? Well, you do it 1, 2, 3, all the way up to n minus 1. So this is going to be n times n minus 1. Because there are n minus 1 n's, and so that's just a simple multiplication at that point. Hopefully, you recognize this from last week. This is Gauss's formula, exactly as it was from last week, in fact. Where, again, Gauss's formula, Gauss-Jordan elimination, Gaussian distribution, etc., etc. right? The summation of natural numbers, 1 up to n, is equal to n times n plus 1 all over 2. We don't go up all the way. We stop short at n minus 1. So if I plug that in for n, then I get n minus 1. And n minus 1 plus 1 is going to be n all over 2. Now rearrange those, and you see that the second one is half the first. So I can simplify this further. And it's simply n times n minus 1 all over 2. Okay? There's the closed form solution for this. That's the ultimate solution that I want, right? It's going to be n times n minus 1 over 2. Now you can go ahead and expand this out, right? And this is going to be 1/2 n squared minus 1/2 n. And you can take it a step further. Which one of these is going to be most important when you... Remember, again, don't lose the forest for the trees here. What we're doing is we're capturing the amount of work being performed here. Well, if we want less work than we want, or if more work is going to be more costly, then we can kind of ignore lower order terms here. Because n squared is way bigger than n. And in fact, subtracting this off, this only makes it bigger. Right? And so again, we're doing a worst case analysis. Bigger is okay because we're getting an upper bound on the amount of work that we're doing. This 1/2 can also be ignored, because ultimately there's a coefficient out front what are we capturing here? We're capturing the the number of comparisons performed by selection sort. Well, what does a comparison cost you? Does it cost you 5 CPU cycles? Does it cost you 0.00001 nanoseconds because your computer's not fast, right? Ultimately, if you move to a computer that's twice as fast, that number will go down even further. We don't care about those numbers. Ultimately, we only care about this number. Right? And so ultimately, in step 5, which is what we're going to cover next time, is that this is an order n squared algorithm. This is a quadratic algorithm. You double the input size, it'll be 4 times as much work. If you go up by an order of magnitude, and it's 10 times as big. You go from an array of size 100 to an array of size 1000. It's going to be 100 times slower, roughly, right? So that's step 4. What about step 5? Again, I'm going to save that for next time because asymptotics, it deserves its entire own lecture. Okay. So step 5, I just gave you a preview of it. We're going to say that it's order n squared and leave it at that, and then we're going to come back to that next time. The last thing I want to do today is let's do one more example. We used that example running through everything before. Let's actually go ahead and use another example that we're already familiar with. What about linear search? My input here is going to be a collection of elements, A1 through AN. And again, I'm being generic. It could be a set of integers. It could be an array list of doubles, right? I'm keeping this general. And a key, K. Right? My output is going to be an element A in A such that A is equal to my key element, right? Note that I'm using the mathematical equals algebra here because it's pseudocode. This is not real code. It would be equals equals, or if you're in a dynamically typed programming language like JavaScript or Python or something like that, equals 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 for strict equality testing. And if you're in most programming languages, you'd actually use a comparator for this if it were not a number. A or compared to K will return something negative, something positive, or 0 depending on whether or not the relative ordering of those things. Right? All right, so just immediately jump into your for loop here. For I, running from 1 up to n, because I'm using 1 indexing here, if a sub I is equal algebraically to the key, then output a sub I. Otherwise, you get through the entire thing, you got unlucky, you didn't find what you were looking for, the needle's not in your haystack. Output what? Right? Now, if this were a real programming language, I would have to deal with this. Do you throw an exception? Do you return null? Do you return a Boolean? False, I didn't find it. Right? What do you return? Well, those are all issues for an actual programming language with an actual implementation for this stuff. Do I return a negative value indicating that the index at which I found it doesn't exist, right? Those are all things that I've seen before in various programming languages. In fact, multiple solutions in the same programming language. Java has several different linear search algorithms that you can use. C has a couple of different ones. What I'm going to do is I'm just going to output a mathematical symbol here, phi, right? So an element A, but I need to document that. So there's still documentation even though it's pseudocode. You can call it pseudo documentation if you want. An element A is such that A is equal to K, and phi if no such element. I'm not saying null because that's a programming language concept. Some languages don't even have null or the concept of null. Some programming languages have null but try to discourage its use and not allow nullable fields, or you can designate something as non-nullable. Some programming languages don't have true and false. C, strictly speaking, C doesn't have true and false. 0 is false and true, and anything else is true. Right? It doesn't have the keywords built into the language itself. Those are add-ons that you can put in that you can add with either a library or with a different standard. But there's linear search. Let's go through our 5-step process, or at least the first 4 steps. Right? 1, the input. I have 2 choices here, remember? Keep it simple, but choose the right one. My input in this case is going to be the collection A. Right? Because if I restrict it to K, then there's no analysis that can be done. The input size is 1, and that's not going to be vary. If you've got a collection of size 1 million versus a collection of size 300 trillion, there's no difference in the eyes of your algorithm if you are choosing your input size to always be 1. It's kind of like a flat function if you tried to map it out, or if you tried to graph it out. My input size, again, good pseudocode. The size of A is going to be the number of elements, n, the number of elements in A. Right? 3, my elementary operation. Right? So there are 1, 2, 3, 4 lines here. And with searching and sorting, the usual go-to is going to be your comparison here. So the comparison on line 2. Right? How many times is that comparison done, my analysis? How many times is this comparison done with respect to the input size, n? Right? Now here's where you can where you need to focus on the worst case scenario, right? You can talk about the best case scenario. The best case scenario would be 1, right? 1 comparison. You get lucky and ace of 1 is equal to K, and you immediately stop and you output. You only performed 1 comparison. You got away with it, right? That's that's overly optimistic. You don't always want to look at it that way. What's the worst case scenario? The worst case scenario is where we go through this entire loop and we make all n comparisons. And you find it either the last place that you're looking for it, ace of n is equal to K, or you get unlucky and you do all of the comparisons. The thing that you're looking for is not in your collection, and so you end up outputting phi. In either case, you're going to do, at most, n comparisons. Right? And again, looking at looking as a preview here, the big O analysis here is simply going to be order n. There are no lower order terms here. There's a constant coefficient of 1 out here, so there's nothing to cross out. I could just say that it's order n. Right? Again, we're saving that for next time. But you might be asking yourself, and this is where we'll end it, well, is there a middle ground here? Best case scenario, worst case scenario. And yes, there is. The naive way of doing this is to simply take the worst case scenario plus the best case scenario and taking their average. Right? 1 half n, right? That's the naive way of doing it. And now, there is a much more not much more complicated, but there is a much more rigorous way of doing this by assigning a probability distribution on the successful key, a successful search on every element in the array. Then a probability distribution on the likelihood that you don't find it, and then you can sum those up. You can maximize it. Blah blah blah. At the end of the day, you can't come up with, coincidentally, you come up with the same thing, 1 half n, right? And this kind of matches your intuition, right? If you've got n elements and you're searching for the needle in the haystack, on average, you're going to search about half of them before you find it, right? And things that are at the beginning, then you have to expend fewer resources versus things at the end. If this one is just as likely to be searched as this one, then they kind of cancel each other out, right? Every one cancels each other out until there's one comparison over here, there are n comparisons over here, there are 2 comparisons for the second one, n minus 1 comparisons for the second to last one, etc. So if you take all of these and you average them all out, then you get about 1 half n, right? About half the size of it. Step 5, though, when you go eventually to big O analysis and you ignore those lower order terms, you still get that it's order n, that it's linear. And that's why we call it linear search to begin with. In the worst case scenario, in the average case scenario, you're going to perform a linear amount of work. If there are 1 billion elements in there, then you're going to perform an amount of work that is proportional to 1 billion. If you go from 1 billion elements to 2 billion elements and you double the input size, then however much work you were doing before, now you're doing twice as much work. If you go from 1 billion elements to 10 billion elements, that's 10 times as big, then you're going to be expecting to you can expect to do about 10 times as much work. The amount of work grows linearly with linear search, right? And that's why we name these things this way, and ties everything together.